In 2007, an undergraduate named David Narkovic at West Virginia University was doing something incredibly boring. He was sifting through old data from the Parkes Radio Telescope in New South Wales, Australia, archival data. Recordings that had been sitting untouched since July of 2001, originally captured during a routine pulsar survey of the Magellanic Clouds. Then he found something, a flash of radio energy, 5 millisecond long, buried in the noise. It was so bright that it had literally maxed out the telescope's sensors, saturating the digitizer across 3 of the 13 receiver beams. His professor, an astronomer named Duncan Lorimer, pulled up the data and, as he later recalled, was speechless. He didn't know what to make of it. His colleague Matthew Bales at Swinburne University in Australia had the same reaction. As Bales later put it, they were completely gobsmacked. The day they discovered it, neither of them could sleep. Even Lorimer's wife and fellow astronomer Maura McLaughlin initially argued the burst wasn't real, that it had to be some kind of instrument glitch. But it wasn't a glitch. That 5 millisecond blip, recorded by a radio dish in the Australian outback 6 years before anyone thought to look at it, became known as the Lorimer burst. And it kicked off one of the biggest unsolved mysteries in modern astrophysics. Here's what made it so disturbing. The signal had a dispersion measure of 375, which is a fancy way of saying the radio waves had been stretched and delayed by passing through an enormous amount of intergalactic gas. Far too much gas to be inside our own galaxy. This signal came from far beyond our galaxy, likely from deep extragalactic space. And it released more energy in 1,000th of a second than our sun puts out in 3 entire days. Then it was gone. Just gone. No repeat, no follow-up, nothing. For years, scientists couldn't even agree on whether this was a real cosmic phenomenon or some quirk of the telescope hardware. The skepticism was intense. In the full decade after the Lorimer burst's discovery, fewer than 35 similar signals were found across the entire sky. Lorimer himself joked that there were more theories about what caused them than there were actual detections. The term fast radio burst wouldn't even be coined until 2013, 6 years after the discovery. Nobody was paying attention. That was about to change. So what exactly are fast radio bursts? They're transient pulses of radio energy lasting typically 1 to 5 milliseconds, thousandths of a second. They span radio frequencies from about 110 megahertz to 8 gigahertz, and they arrive from random directions across the sky, confirming they come from far beyond our galaxy. Their sources are physically tiny. Based on the speed of light and the burst duration, the emitting region is inferred to be no larger than a few hundred kilometers across. That's smaller than a mid-sized city, producing more energy than the sun. And the energy numbers are genuinely staggering. An average FRB releases the same energy in a single millisecond that our sun produces in 3 full days. The brightest ones match the sun's yearly output, packed into the time it takes you to blink. The most extreme FRB ever measured in terms of raw energy, a burst called FRB 202-20610A, detected in 2022, released the equivalent of the sun's output over 30 years in a millisecond. The population spans roughly 8 orders of magnitude in energy, from the weakest nearby bursts to absolute monsters that rank among the most energetic events in the observable universe. And here's the part that makes your brain hurt. The signal that actually reaches Earth after crossing billions of light years has been described as 1,000 times weaker than a cell phone sitting on the surface of the moon. The fact that we can detect them at all is a testament to how mind-bogglingly powerful these things are at their source. Scientists figure out how far away FRBs come from using something called dispersion measure. As radio waves travel through the thin ionized gas between galaxies, lower frequencies get slowed down more than higher ones. So by measuring the delay between the high and low frequencies in a burst, you can calculate how much gas the signal passed through, and from that, how far it traveled. Think of it like light splitting through a glass prism, except the prism is the entire observable universe. By 2020, this technique was formalized as the McCourt relation, and it's since been confirmed across more than half the observable universe. FRBs became cosmic rulers, measuring the invisible stuff between galaxies just by passing through it. And this is where the story takes a turn nobody expected. In 2012, the Arecibo Observatory in Puerto Rico, that massive 305-meter radio dish built into a natural sinkhole in the jungle, picked up a new burst. Astronomer Laura Spittler at the Max Planck Institute for Radio Astronomy reported the detection, catalogued as FRB 121102. At first, it looked like every other one-off flash. Interesting, but just another data point. Then in 2015 and 2016, Paul Scholz at McGill University found 10 additional bursts coming from the exact same spot in the sky. Same coordinates, different times. When his team published the findings in the journal Nature in 2016, it sent genuine shockwaves through the field. This was the first fast radio burst ever confirmed to repeat. That single fact blew the whole thing wide open, because if something repeats, it means whatever created it survived the event. You cannot destroy something and have it keep sending signals months later. That immediately ruled out one-time catastrophic explanations like two neutron stars colliding. Something was alive out there, still firing. FRB 121102 was traced in January 2017 to a tiny, irregular dwarf galaxy sitting 3 billion light-years from Earth. The burst source sat within a bright, star-forming region, accompanied by a mysterious, persistent radio glow that never switched off. Its environment was extreme. The Faraday rotation measure was around 146,000, indicating the signal was passing through hot plasma wrapped in an absurdly powerful magnetic field, about 500 times higher than any other FRB at the time. And this thing was prolific. China's FAST telescope, the world's largest single-dish radio telescope, nestled into a natural karst depression in Guizhou province, detected 1,652 bursts from this single source during just one monitoring campaign. One location, over 1,600 signals. Something out there was screaming into the void over and over again. But here's the detail that everyone missed at the time. Repeating FRBs behave differently from the one-off bursts. They produce wider pulses, emit over narrower frequency bands, and display something scientists dubbed the sad trombone effect, where the signal slides from higher to lower frequencies within each burst like a deflating balloon. Whether repeaters and non-repeaters are truly two different populations, or just the same thing observed at different activity levels, is still one of the biggest debates in the field. Instrument that turned FRBs from a niche curiosity into one of astronomy's hottest fields isn't some billion-dollar space telescope. It's 4 enormous half-pipe-shaped metal reflectors sitting in a field near Penticton, British Columbia. The CHIME telescope, short for the Canadian Hydrogen Intensity Mapping Experiment, was originally built for cosmology research. Nobody designed it to hunt FRBs, but it turned out to be an absolute detection machine. Each of its 4 cylindrical reflectors stretches 100 meters long by 20 meters wide, with 0 moving parts. CHIME stares at the sky and lets the Earth's rotation sweep the heavens past it, observing 3/4 of the entire sky every single day while processing 7 terabits of data per second. Before CHIME, scientists knew of maybe 30 FRB sources total. The second CHIME catalog, published in January 2026, reports 4,539 bursts from 3,641 unique sources. That includes 981 bursts from 83 confirmed repeating sources. CHIME detects roughly 2 to 3 new FRBs every single day. From those detection rates, astronomers estimate FRBs may occur somewhere in the observable universe, roughly every minute. Victoria Caspi of McGill University, who leads the CHIME-FRB collaboration and was named one of Nature's 10 most important people of 2019, was blunt about the state of the science. None of the models that had been proposed seemed perfectly adequate, she said. Not one really explained all the observations. And that brings us to the signal with a schedule. FRB 2018-0916b, nicknamed R3, doesn't just repeat. It repeats on a clock. In June 2020, the CHIME team published a landmark finding in Nature showing that this source follows a 16.35-day activity cycle. It fires off bursts for about 4 to 5 days, goes completely silent for roughly 12 days, then starts up again, like clockwork. This pattern has held steady across more than 100 cycles over multiple years of monitoring. It gets stranger. Bursts at different radio frequencies arrive at different phases of the cycle. Higher frequencies show up earlier in the active window, lower frequencies arrive later. Scientists describe this as chromatic windowing, and it puts brutal constraints on any theoretical model trying to explain it. Some researchers think the magnetar might be orbiting a companion star, and the periodic window opens when the magnetar swings to the part of its orbit facing Earth. Others think the magnetar itself might be wobbling, like a spinning top that's slightly off-axis, pointing its radio beam toward us only during part of its precession cycle. And the source itself sits in a spiral galaxy much like our own Milky Way, a relatively cozy 500 million light-years from Earth. Not some exotic environment, not some extreme dwarf galaxy. A normal-looking galaxy, with a signal that runs on a schedule we can predict down to the day. Something out there is following a pattern, and we still cannot fully explain why. If you're finding this as fascinating as I think you are, hit subscribe. I cover space and science stories like this regularly, and trust me, the discoveries keep coming. Alright, so here's where things get really interesting, because in April 2020, while the rest of the world was dealing with lockdowns, a magnetar inside our own galaxy decided to make history. On April 28, 2020, a known magnetar called SGR 1935+2154, located about 30,000 light-years away in the constellation Vulpecula, erupted. Two completely independent radio systems picked up an extraordinary burst at the same time. CHIME detected it across 93 of its 1,024 receiver beams at frequencies between 400 and 800 megahertz. And STARE-2, a modest 3-antenna array spread across California and Utah led by Caltech astronomer Srinivas Kulkarni, caught it at 1.4 gigahertz. The burst was 4,000 times more energetic than any radio pulse ever recorded from the famous Crab pulsar, and it was 1,000 times brighter than any previous magnetar radio emission. The day before, NASA's Swift Space Telescope had detected a violent storm of X-ray bursts from the same magnetar. ESA's integral satellite then confirmed simultaneous X-ray emission from the radio event, providing the first ever connection between radio and X-ray bursts from a single source. 3 landmark papers appeared in Nature on November 4, 2020. Caltech graduate student Christopher Bochenek led the STARE-2 paper. It was official. This was the first fast radio burst ever detected inside the Milky Way, and the first ever linked to a known astrophysical object. Jason Hessels of Astron and the University of Amsterdam summed it up perfectly. Without overusing the word breakthrough, he said, "This really is a breakthrough." So what is a magnetar? It's a type of neutron star, the ultra-dense remnant left behind when a massive star explodes in a supernova. Imagine cramming the mass of our entire sun into a ball about 20 kilometers across. A teaspoon of that material would weigh about 1 billion tons. Now give that ball a magnetic field roughly a quadrillion times stronger than Earth's. A field so intense that if a magnetar sat halfway between the Earth and the Moon, it would wipe every credit card on the planet. That's a magnetar. Only about 30 known magnetars, including candidates, have been identified in our galaxy and the nearby Magellanic Clouds, making them among the rarest and most extreme objects in the known universe. The leading model, developed by Ben Margalit and Brian Metzger at Columbia University, proposes that when these things flare, they produce coherent radio emission either from within their own magnetosphere or through relativistic shock waves smashing into surrounding material. A 2024 study even found that FRB energy distributions resemble earthquake aftershock patterns, suggesting magnetar starquakes, literal fracturing of the neutron star's crystalline crust, could be a trigger mechanism. But there was a catch that kept the mystery alive. The Milky Way magnetar burst was still far weaker than the most powerful extragalactic FRBs. The CHIME team estimated that a magnetar like this might produce a truly FRB strength burst only once every 500 years. Whether the same mechanism can scale up to explain the most powerful bursts from billions of light years away remained a very open question. And then 2024 and 2025 delivered discoveries that made the whole picture even messier. In March 2025, CHIME and its newly completed Outrigger array, a system of stations stretching across the continent, detected the brightest fast radio burst ever recorded. It was designated FRB 202-50316A, but scientists gave it a nickname that perfectly captured the moment: RBF LOTE, radio brightest flash of all time. It was traced to a spiral galaxy called NGC 4141, just 130 million light-years away. In cosmic terms, that is basically next door. As MIT's Kiyoshi Masui noted, cosmically speaking, this fast radio burst is just in our neighborhood. The precision was extraordinary. They pinpointed the source to within 42 light-years, the finest localization ever achieved for a one-off FRB. And then the James Webb Space Telescope turned its infrared eye on the exact spot and found a faint source. That could be one of the clearest compact counterparts ever identified at an FRB site in another galaxy. But here's the part that doesn't add up. CHIME has been watching that patch of sky daily for over 7 years. RB float has never repeated, not once. If all FRBs come from magnetars, and magnetars can fire multiple times, why has the brightest one ever recorded stayed completely silent since? That reopens the door to one-time catastrophic origin theories. Maybe something died in the process of screaming across the universe. And if that wasn't enough, there's the signal that broke every existing model. FRB 20240209A was first detected in February 2024 and went on to repeat 22 times through July. When astronomers traced it to its host galaxy, they found something that was supposed to be flat-out impossible under standard theory. The burst came from an approximately 11 billion-year-old quiescent elliptical galaxy with essentially no ongoing star formation. A dead galaxy, one where no massive stars have exploded in billions of years. The burst location sits 130,000 light-years from the galaxy's center, the largest offset ever measured for any FRB. Young magnetars require recent supernovae to form, and dead elliptical galaxies simply do not have those. Northwestern University Wen-Fai Fong captured the feeling in the astronomy community perfectly when she said that just when you think you understand an astrophysical phenomenon, the universe turns around and surprising you. Now, I know exactly what some of you are thinking. Has anyone considered that these might not be natural? The alien hypothesis is actually more legitimate than you'd think. In 2017, Harvard astrophysicist Avi Loeb and Manasvi Lingam published a real peer-reviewed paper in the Astrophysical Journal Letters proposing that FRBs could be beams used to propel enormous light sails across intergalactic distances. They calculated that the required transmitter would be about the size of a large, rocky planet, which Loeb described as intriguingly plausible. He argued that an artificial origin is worth contemplating and checking. Astronomer Matthew Bales called it a delightful thought experiment, but also an incredible long shot. And the 2020 Magnetar confirmation significantly weakened the case. We now know for certain that at least some FRBs come from natural sources. But Loeb has pointed out that confirming one natural source doesn't rule out artificial origins for others. The honest scientific answer is that it's unlikely, but technically not impossible. What is certain is that FRBs have already become one of the most useful tools in astrophysics, regardless of what creates them. In June 2025, a landmark study used 69 precisely localized fast radio bursts as cosmic flashlights to solve a mystery that had haunted cosmology for decades: the missing baryon problem. Scientists knew exactly how much ordinary matter should exist in the universe based on Big Bang calculations, but telescopes could only account for about half of it. The rest had seemingly vanished. Using FRBs as probes of the invisible gas between galaxies, the research team found the answer. Roughly 76% of all ordinary matter in the universe is floating as superheated, invisible plasma in the vast filaments of the cosmic web between galaxies. It was hiding in plain sight the entire time. We just needed the right flashlight to find it. That same study identified FRB 20230521b at a staggering distance of roughly 9.1 billion light-years, making it the most distant FRB ever detected. Its light has been traveling for about 2/3 the entire age of the universe. So where does all of this leave us? We know magnetars can produce fast radio bursts. That's confirmed. But the dead galaxy repeater from a quiescent, approximately 11 billion-year-old elliptical galaxy with essentially no star formation shouldn't exist under that model. A repeating FRB inside an ancient globular cluster of galaxy M81, where no young stars have formed in billions of years, shouldn't be possible either. Jason Hessel's was direct about the implications. If what we're looking at really is a magnetar, it can't have been formed from a young star exploding. There has to be another way to make one. There's also the cosmic heartbeat that still confuses everyone. FRB 2019-1221A, detected by CHIME, lasted an unprecedented 3 seconds with 9 distinct peaks, separated by 216 milliseconds. Like a heartbeat from across the cosmos, it remains the longest duration FRB with clear periodic substructure, and nobody has a clean explanation for it. One 2024 statistical study, after correcting for observational biases, suggested the true repeater fraction could be much higher than what we observe directly, potentially exceeding 50%, and maybe even approaching 100% once you account for selection effects, which means every FRB we've ever classified as a one-off might just be a repeater we haven't watched long enough. Or maybe RBF Float's 7 years of total silence tells a different story entirely, and we need at least 2 distinct classes of sources to explain what we're seeing. In December 2025, astrophysicist Bing Zhang proposed a unified model where all FRBs come from magnetars, but magnetars formed through wildly different pathways. Isolated ones gradually lose alignment between their spin and magnetic axes, producing rare one-off bursts. Magnetars orbiting companion stars maintain alignment through material falling onto their surface, enabling them to keep repeating for years. One phenomenon, multiple origin stories. It's elegant, but even Zhang acknowledges it doesn't explain everything. New instruments are about to transform the field completely. The Cord telescope in Canada is installing 512 dishes with roughly 10 times CHIME's sensitivity. The DSA 2000 in Nevada, with 1,650 dishes spread across a desert valley, is projected to find 10,000 FRBs per year with precise localizations. And the Square Kilometre Array under construction across South Africa and the Australian outback will push detection limits to the farthest edges of the observable universe. Emily Petroff, one of the field's leading researchers, captured the eternal frustration and excitement perfectly. Every time we find a new one, she said, it's different. There's so much variety, it keeps us on our toes. We went from one bewildered astronomer staring at a 5-millisecond blip buried in 6-year-old data to over 4,000 detections, a confirmed natural source, and a tool capable of finding the universe's missing matter. The signals keep coming, the mysteries keep deepening. Something out there is screaming into the void across billions of light years of empty space. We've started to figure out what. We still don't fully understand why, and that is what makes this one of the most exciting frontiers in all of science right now. If you want to keep exploring the biggest unsolved puzzles in the universe, there's a video on screen right now that I think you'll love. I'll see you there.